Welcome back to my 5th GLSL tutorial, and in this video I'm going to talk to you about the normal mapping, or otherwise called bump mapping. By the way, you may notice that my theme has changed. Actually, my whole operating system has changed. I swapped from Ubuntu to Debian, and I have slight technical difficulties with it. That's why this little delay between the tutorials. And yeah, it's a pretty user-friendly operating system, just it chooses its friends very carefully. Anyways, back to the subject. So the bump mapping is basically a technique where you use different normals on the surface to fool the lighting calculation that there is a bump there. So here is a bump, for example, made from vertices. As you can see, this is made from a lot of little vertices. So if it would be a 3D wall, something like this, it's a 3D wall, as you can see. Then here is a little bump there in the wall. Now this little bump could be made with a lot of small vertices. So for example, from 4-vertex, which was the original wall, you go and subdivide it by 10 or 11 times, and you have 1 million vertex, and you made a very nice bump in the surface. Of course, that's a working solution, but the problem is that still nowadays the video card can't handle that much of vertices, since video cards have a finite capabilities of processing vertices, cannot process that much of vertices. Of course, if you just increase it to 4000 vertex instead of 4, it can handle it, your video card can handle it, no problem there. But if you change it to every single wall, every model, everything into a lot of vertices, so subdivide it by a lot and add vertices, sometimes. So after some number of vertices, your game starts to lag, and obviously that's a problem because no one wants to play a game which is run with 1 FPS or something. So that's why there is this technique called normal mapping. Here it is. As you can see, we modify the normal vectors instead of the actual surface. So our surface still consists 4 vertices, so if it is again a 3D wall, as you can see. By the way, it's not just work if there is a simple plane or wall, but it actually works if you have a complex weapon model, as I will show you in the end of this tutorial. So how can we store these normal vectors? Because obviously we need to store the normal vectors so we will know where the bumps are. Okay, by the way, there are a small fact that you shouldn't use the bumps which are too big. You should always use a little bump. You will see in a moment what I mean, but if there I will demonstrate it. It will be probably clearer on that way. So we can use a texture to store the normal vector, or this is otherwise called normal map or bump map, probably both. Anyway, so you use the R, G and B component of this normal map to store the actual vector. So your R component will be the X component of the vector, your G component, obviously the green, will be the Y component, and the blue component will be the Z component of the vector. So in this way you can store a vector in the R, G and B component of the image, which is a very convenient way to store it because you can easily modify a normal vector like that with GIMP or Photoshop or some other image manipulation program, and you can create normal maps with GIMP, Photoshop or Blender or other 3D programs. I will show you how to create normal maps in GIMP and in Blender, because these are 2 free programs which is capable of creating any kind of normal map. Obviously a Blender will generate a better normal map, but it will take a longer time because you have to create a model which you actually model those little bumps, and the Blender will find out where are these bumps and make it into a normal map. While GIMP, you just open up the image and use a normal map add-on, or what does it call, plugin, yes, that's right, a plugin in GIMP, and it will pretty much try to figure out where are the bumps. So I will show you both programs, and yeah, that's pretty much it. Let's go. So how does it look like? It looks like this bluish image. For this image, it's usually a bluish image. There is a reason for that, and the reason you will see in the next or some other dia in this little presentation is because these vectors are stored in something called a normal space. So let's see what normal space is. No, not now, but in a later video. So yeah, that's I pretty much already told. One important thing is that the zero component of the vector, so when there is so the zero component of the vector is pretty much the middle component of the color, because obviously the colors are stored in either 0 to 255 in case of a 8-bit per component image, and in this case the 0 vector will be 127. or in OpenGL and GLSL it is converted to 0 and 1, not depending how much bit per component you have. It's always 0 to 1. And in that case 0.5 will be representing the 0. Now the question is how we can convert a number from 0 to 1 to -1 to 1, because obviously we want the normal vector to be able to point into the negative directions as well, so the negative x direction, the negative y direction, and so on. So how can we do that? It's a pretty simple question. We just multiply it by 2, so we get a number which is between 0 and 2, and then subtract 1 from it, and we get a number which is between -1 and +1. That is, it is just as simple as that. For example, try it with 0. 0 times 2 is 0, -1 is -1. Try it with 1. 1 times 2 is 2, -1 is 1. It is just as simple as that. Okay, let's see what the next is. Okay, the tangent space. It's a special space where these normal, which are these normal vectors used. You will see that this tangent space, so according to the definition, this tangent space is a space where any given point which you are calculating with at 0, 0, 0 coordinate, and the normal vector is facing at 0, 0, 1 coordinate. Obviously the unmodified normals, I will return to what unmodified and modified normal will be mean. So we already know the position and the normal vector. We need 2 more data to do the lighting, because obviously normal mapping, I didn't say that, doesn't make any sense without per pixel lighting. So if you don't have per pixel lighting, you probably should go back and watch that tutorial or get some code for per pixel lighting, because as I said, it doesn't make sense without it, because that's what makes it cool. Anyway, so we have to calculate 2 more vectors in order to make everything work, because the per pixel light calculation needs position to the light and the position to the viewer, these 2 vectors additionally, if you remember, and the normal vector. But we already know the normal vector, because the normal vector is facing a 0, 0, 1 direction and the given point at 0, 0, 0 position. So we have to calculate the view position and the light position in the tangent space. How can we do that? We basically get a transformation matrix. I will show you in a later video what's that transformation matrix. Multiply the light to the light position and the view position with that vector, and we get the tangent light position and tangent view position. Okay, that's pretty much it. So let's go to the next. Okay, so here is a little example, and as you can see, here is a face of the, I don't know, some wall or something, and then we pretty much just transform it, so it will be 0, 0, 1 coordinate, the normal vector. The view vector will look here and here. So basically we just do a little bit of rotation and actually translation as well, but translation we don't really care about that. So the angle remains the same between the vertices, so the light calculation will work exactly the same as previously. That's pretty much it. So so the lighting calculation not change, only the direction of the light vector and the view vector will change. That will be pretty simple to implement in the fragment shader, because we have to modify 2 or 3 things in the whole fragment shader, because we just have to modify where the new light vector is, where the new view vector is, and where the new normal vector is, and pretty much the rest of the light calculation is will be the same. So that's what I wanted to represent with this little transformation thingy. So we just basically rotate it, but the angle between the vertices vectors will not change, so the light calculation will be exactly the same as previously. So what is the transformation matrix? Without explanation, I just write it down here. So the tangent vector, the bitangent vector, and the normal vector. I will show you in the next video what the tangent, bitangent, and normal vector mean. And by the way, it's binormal or bitangent. It's called both. Anyway, so this is the transformation matrix. If you multiply a vector or a vertex with this matrix, then you get it will go into tangent space. So let's see in the next video what are the tangent, bitangent, and normal. By the way, I will, if you're interested in the mathematical part where this matrix actually come from, I should put a link in the description where it will explain the mathematics behind this matrix. But you don't really have to care about the mathematics, because it's work, it's there, it is it, so you don't have to really know where does it came from. But if you are interested and curious, then let's go for it. Okay, so what are these vectors basically? The normal vector, we already know the normal vector, so here this n is resolved, we already know what the normal vector is, right? Then, what else? The bitangent or normal vector is actually a vector which is perpendicular to both the normal vector and the tangent vector, so we can easily calculate that with the cross product, because the cross product will give back a vector which perpendicular to the other 2 vectors. which you get as a parameter. So we know the bit tangent vector, so this is the cross product between the normal vector and the tangent vector. Okay, the last thing is remaining the tangent vector. You can actually, this tangent vector is a vector which lying on the surface basically. So here it is a little example. Your object is probably built up from small polygon like triangles. So the tangent vector the tangent vector for A, by the way, there is a tangent vector for every single vertex on your object. So the tangent vector for A is actually either be the C minus A or the B minus A. So these two vectors which are on the surface. Or you can even average these together and then normalize them. So it will be something like this. So I think it's work either way. I'm not sure, and I'm not really sure. I haven't tested this technique too much, but I'm pretty sure it's supposed to work. But I will not do that in this tutorial. I will do a little bit of cheating because I know that some of you are not here from my OpenGL tutorial, so you might not have this OBJ loader file. And in this case, I will actually use a little bit of cheating to approximate this effect. By try to find a vector which is perpendicular to the normal vector. How can I find a vector which is perpendicular to the normal vector? I actually try to use the cross product, because the cross product will give back a perpendicular vector to either the 0, 0, 1 or the 0, 1, 0 coordinate. So this is the positive, this is the z and the y-axis. So it will pretty much try to give back a perpendicular vector to both, and the cross product will return actually a null vector if the normal vector is equal to the second parameter, or the first parameter equal to the second parameter. In that case, I will actually try to find the longest vector. So either this one is the longest, the first one, or the second one, and I will try to use that as a normal vector. So basically I will just try to find a perpendicular vector to the normal, and if the normal vector is 0, 0, 1, then I will choose the 0, 1, 0 basically, because obviously I don't want to calculate with a null vector. And by the way, here where I get this idea, so check this link out if you want. This is where it's this little thingy about calculating the normal vectors. And after a little testing, I actually find out that for some reason it will not give the right result. I mean, it gives the right result, but actually the opposite right result, which is the wrong result. Anyway, so if I put a minus sign right here and right here, so I will not use the 0, 0, 1, but the 0, 0, minus 1 and the 0, minus 1, 0, then it will actually give back the right result. Why? I have no idea, but it's working. Anyway, what is the next? Yeah, of course, it's time to show you how to create one of these normal maps in GIMP or Blender. By the way, don't worry if you don't get everything. I admit this is a long material, this is a kind of advanced subject, so might you get later in the code, or you can come back to the beginning, or you can read an article about it. Anyway, just stick with it and I will go to coding, maybe that will be clearer. So, thank you, of course, I go to GIMP and Blender. Well, so let's start with GIMP. So you have to download a plugin for GIMP which is called GIMP Normal Map. I'm pretty sure if you go to Google and write GIMP Normal Map, that will be the first result which will come up. If you're using Windows, then the life is easier for you because there is an executable, downloadable executable. So I guess you just run the exe file and it will install it automatically. If you are using some other operating system like Linux or Mac, you have to compile it from source code. This little install guide gives you what needs to be do in order to install this. Pretty much you have to install all of these packages in order to make it work. So if you are using Linux, just use the apt-get or aptitude to download this. So for example, sudo apt-get install, and you need GIMP 2.4, but actually you don't need the GIMP, you need the development file. So just write libgimp and just press to tabulator, and it should give up what you want to install, and usually you want to install the development version. So just install the GIMP, libgimp, libglib, gtk, libpango, libatk, pkgconfig, libgtk, glx, and libglue libraries. And if you install all of that, you can install the actual plugin. How you can install the actual plugin? In Linux, you just go into the folder, so the GIMP normal map folder, and write into make. And after that make is finished, you just write into make install. That is it, and in theory after that it should be installed. If you still don't find it in your game, so this plugin, then you have to manually copy this executable, which will be here called normalmap without extension, to your folder. So you go to the own folder here and make sure you show the hidden folders and files, and just search GIMP 2.6 and just put it into your plugin folder, like I did here. Like as you can see, I put the normalmap executable right here into my plugins folder. So now if I open up GIMP and I exit from this, let's open up an image actually to demonstrate. So I go to my desktop and search for my GLSL tutorial folder, and I will actually open up this brick.jpg. So I will open up, and as you can see, this is how it looks like. This is I show you already as a texture. So let's make a normal map for this image. So to make a normal map, you actually one moment. Okay, I just changed it to English so I can explain what menu. So you go to the filters and you go to the map, and you go to the normal map. This is it, and it is just as simple as that. Here you can change a lot of crap, and for example you can change this scale to make the bumps bigger. So let's make it bigger. I will make it 3.0 anyway, and I just press OK, and as you can see, it's converted into a normal map. Not too nice normal map, but actually we can save it. It will be good for some demonstration. So I will save it to the GLSL tutorial, and I will call it bricknormal.bmp. Right. And okay, right, so this was the GIMP way of doing it. It's pretty simple. You just open up your image, go to your filters and map and normal map, and it will generate a normal map for any image. At least it will try to generate a normal map for every image. Of course it will not be perfect, but now let me show you the Blender way of doing things. So in Blender you have to actually create, let me open up Blender, you have to actually create two models. One is the low polygon model, which you actually want into your game, and one is a high polygon model, which you want to basically map to your low polygon model. So your low polygon model will look like your high polygon model, but it will be still low polygon. I don't know if it makes sense or not, but I will show you. Okay, so I will actually just do it with a plane. Of course it works with a weapon or a zombie model, anything you can imagine, but I will do it with a plane because my time is limited right here in this tutorial. So oops, I just press space and add a plane. And I just rescale it, resize it with the S. Okay, and actually let me duplicate it. So I just press Shift D and press Escape. Because the Escape, the two planes will be exactly the same place. As you can see, this is exactly the same. You cannot even tell if there are two, but actually there are two of these. So now let's choose one plane and add a multi-divide. So I go here to the object modifiers and add a modifier and subdivision surface, and I will do a simple subdivision, and actually let's slide up this value to 6. Actually let's make it 7, or the slider will go to actually 6. You can, if you click here at the center of this slider, you can actually write 7 right there. Okay, so now I have a pretty high detailed plane. It's actually just a big subdivided plane. So now that I have this, let me actually modify this. So let's apply this modifier with the apply button, and as you can see there are a lot of little quads right here. So let me do something with these quads. I will actually make some form from this, so it's like the terrain. Okay, to do that I will press A to deselect everything, C to get this little actually go to press 7 in your number pad to go to top view, press C to get this little circle thingy which you can use to select, and you just select something from this. So I will just select this. Okay, and actually I will now activate this proportional editing mode. Right, so activate this, and here this next fall off type for proportional editing mode, I will change it to sphere. Right, and now if I want to if I move these vertices right here, it will not only move those vertices, but it will move even the not selected vertices. So let me show you. As you can see, and if I press if I use my mouse scroller, I can actually set the radius of these, as you can see. Anyway, this should be okay. So as you can see, I just make this little object. If I press A, this is how it is look like. So now I will make the simple 4 plane into this this little smiley thingy. Okay, so to do that, first of all you have to select the low polygon plane, which is in my case the plane, and actually let's add UV texture for it. So here I will just open up a new tab, or divide, or whatever it's called, split areas, and I actually use this little thingy right here in the top right corner to make a new tab, and I will just open up the UV image editor and I create a new image. So new image, this is just as simple as that. You can change the size. Actually I will change the size to 512 by 512 and just press OK, and it will create an empty image. So let's actually unwrap this little, so let's actually add the UV coordinate. So I will just go to edit mode by pressing tab and use the U and unwrap. That's it. I have unwrapped this little image right here, this quad right here, into this image. Now the last thing is remaining to do. If your models are not actually in the same place, just put them into the same place by pressing Alt L, I believe, or Alt G or something like that, and then select your high model first, and then use the Control key to select your low model. And actually both should be selected by now, but I'm not sure about that. So use your Shift key to select the high and low, not Control Shift, and go to your camera or render tab, and here just go down here and there will be a bake tab right in the bottom. So I will open up that, and here in the bake mode I will select normals. As you can see that I can choose a lot of things right here, like ambient occlusion, shadows, normals, textures, so on so forth. I will choose the normals right here, and then I go right here and I will check the select to whatever. I will take a look, select to active. I have to check this, and pretty much I am ready. So I just press bake, and if everything goes correctly, I get a normal map right here. As you can see, this is my normal map. Let me save this as well. So I go to image, and here I will just save as image, and I will go to our project folder, so the GLSL tutorial, and I will save it as smile.png. Okay, pretty much that was it. You can escape from this program right now, and we have the normal maps in our project folder right here. So we have this smile, actually smile. Anyway, so it actually doesn't look so good because you probably need to use more subdivision. But anyways, and here I have this brick normal, which is again pretty ugly. I should use another image or something because these two are kind of ugly. Anyways, so let's go to the programming. I know that you are eager to start it. So okay, I am back in my text editor and we are finally started coding. This is the same program as we had earlier. Let me prove it by running it. As you can see, only difference actually is that I added this parenthesis, although I forget to add this parenthesis, but I should have added this parenthesis because as I added an annotation in the last video, we have to add this parenthesis so the ambient and the diffuse light will be affected by the attenuation factor anyway. So it's a little bit different result, but kind of similar. And let me actually lower a little bit this factor by so like that. So we will still have a specular light, a kind of colorful, so a kind of strong specular light. As you can see, it's a very strong specular light. Probably it will be some other value would be okay, but for now the normal mapping we need strong specular lighting, so we will see the actual effect. Right. Actually, I have downloaded two other images from the internet. This test1.normal image right here. This is it. As you can see, it's a much better, much higher detail than we made in this PNG, but probably it's made in the same way. So open up Blender and some program, make an image like this in high quality and make this normal map as I showed you. And actually there is a texture for that as well right here. So we will, first of all, let's apply this texture. So let's not go into the normal mapping. First of all, let's just add the texture. It's a simple test because we already did that. So here in the init function we actually load two textures. So let me load the test1.bmp file, which is this right here. So test1.bmp, and let me load as the second texture the normal map. So the normal map is test1 normal. So test1 normal.bmp. Perfect. Okay, I have loaded the two images, so let's add it to the texture, let's add it to the shaders. So I will use a GL uniform 1i to give it as a sampler. Okay, right here, 1 1i. Okay, 1i because we give an integer, and I will create a sampler 2D right here in the fragment shader called img. That will be the 0 text, that will be on the 0 texture unit. Let me activate it. So gl active texture and gl texture underscore gl texture 0. Okay, and let me bind this image as well. So gl bind texture gl texture 2D because it's 2D image and it's called my img. Okay, and let me give the normal map to the shader as well. So I bind it to the first texture unit. Actually, this is the second, depending on if you're counting like C++ or you start from 1. And this is called my img2 because my img2 right here is storing the normal map. Okay, and pretty much that's it, and we change it to 1 because this is in the first texture unit. So let me create these uniform sampler variables right here in the fragment shader. So in here in the top, let me make sampler, actually this is a uniform sampler 2D because 2-dimensional texture, and one is called img, and let me make another one which is called, what did I call it? Oops, I forgot to change. I call it normal map. Okay, I call the second normal map right here. For now I will not use this normal map yet, I will just simply use the texturing. Okay, and actually we need to apply the texture coordinate as you have seen in the texturing tutorial. So from the vertex shader, let me create a vector 2. So varying vec2, and I just call text coord because this will be the texture coordinate, and let me just pass the texture coordinate here. So text coord equal gl underscore multi text coord 0. Simple enough. So I just give the texture coordinate to the shader as well, so we know how to texture it to whatever object we have. In that case I have a simple plane. So in the fragment shader, as I said in the lighting tutorial, to make this lighting to be applied to whenever you have a textured object, you only have to do is change the material color for the diffuse and the ambient to the texture color. So let me do that. I will create a vector free, and I will call it text color because this will store the texture color obviously, and it will be I will convert it to vector free because texture 2D will return a 4-dimensional vector because it's returning with the alpha component as well. So texture 2D, and it's waiting for the image and the texture coordinates which I call text coord. Simple enough. I have the texture coordinate, so I will just change the material ambient property and the material diffuse property to the texture color. And that pretty much should be it. So let me try to compile it. I can guarantee that it will work, but it's a nice try at least. Okay, so let me run this, and it indeed doesn't work because we have an implicit cast from vector 4 to vector 2, and I know what I screwed up in the vertex shader. Right here the GL multi-text coord is actually a 4-dimensional vector, so let me just get the XY component from that. So the first two components, we don't care about the other components, and indeed now it is working, and as you can see we have the image and we have the specular. By the way, you could change the material specular property to this texture color, but it will not give that nice result. It's better to have a different material specular and basically separate the specular from the other properties, because the specular is always some light or some white or some very shiny color. Right, so let me actually start to coding the normal map. So right here, first order of business is to actually get the tangent vectors. Usually you will give it as an attribute variable, so you create an attribute vector free and tangent. But as I said, I will cheat a little bit and I will calculate it, although that is a much better solution, but I know that some of you are not here from the OpenGL tutorial, so I will not want to go into the object loader and calculate there. So I will just calculate it right here. Okay, to calculate it, as I said, we need two vector, and we have to cross product this because we want a vector which is perpendicular to the normal. So let me create a vector free, and I call it tangent. Okay, and actually we have to, so as I wrote right here, not right here but right here, we actually have to use the cross product between the normal vector and this vector, so it's the base vector 0, 0, 1 or 0, 1, 0. So I cheat a little bit and I get the idea from this page right here. So check that out, probably there is a better explanation there. So let me make it right here, so vector free and v1, and this will be the cross product between the gl underscore normal. By the way, this normal is the unmodified normal according to the page, so we don't multiply between the normal matrix yet, and the vector free, which is 0.0, 0.0 and minus 1.0. Right, and let me create another one of these vectors. This will be, or the only difference is that this is the -1 is the y coordinate, and I call it v2. Right, so I have to get the longer one, because as I said, if my normal vector is actually looking at the 0, 0, -1 direction, then actually it will give back a null vector, and obviously we don't want to calculate with a null vector, but in that case this second will be give back a longer vector, actually a normal vector in that case. So we get the longer one basically. So if v1 is length v1, length give back the length of a vector greater than length v2, then we just simple set the tangent equals to v1 as the tangent is equal to v2. As simple as that. So we just basically calculated the tangent vector. As I said, this other solution when you give it as an attribute variable is a little bit better, but it's still working as so according to the testing it is still working. Right, so the next order of business is to actually create free vectors. So vector free, and this will be first normal, actually call it n, and this will be the GL underscore normal matrix times GL underscore normal. So we just get the normal vector, and actually let me normalize this so we will make sure that this is indeed a normal vector. So normalize an I. Okay, let me create another one, vector free. This will be the tangent vector. The tangent vector is similar in some way to the normal vector in the way that we don't want to apply translation to it, but we want to apply rotation and scaling and so on to it. So it actually has the same matrix, GL normal matrix. So actually let me copy this. Not this, but just this one. Oops, just this one. Okay, so I get the normal matrix and I multiply it by the tangent which we have calculated, tangent. Right, and the last is the b tangent vector, so let me create that, vector free, and b, I call it b, like b tangent. Vector and the b tangent vector, as I said, is just the cross product between the normal vector and the tangent vector. So I will use the cross, and here I will pass the normal and the tangent vector like this. This is just as simple as that. The cross product will give back a vector which is perpendicular both to the normal vector and both to the tangent vector. And actually it is unit length long. I believe we don't have to normalize it because the input parameters were unit length long. So I believe this one should be a unit length long vector. And we don't have to multiply it by the normal matrix because we are already in the right place, right space. Anyway, so I just calculated the normal, tangent and bitangent vector, and let me create a matrix from this. So this is matrix 3, and I just call it math or whatever. And actually let me initialize it right here. So I use the constructor. Okay, and here let me open up that GIMP and show you the matrix which we have to create. Not this one, this one. Okay, so the so we have to basically do whatever I wrote in here. So tangent x, bitangent x, and normal x. So let me create this. T.x and b.x and n.x. This is just as simple as that, and let me do the same with the y coordinate. So this is y, and the z coordinate, z. Right, I have a matrix which is basically the matrix for the transformation to the tangent space. Now I only have to do is basically get a vector which pointing to the light position, so we get the surface to light vector basically, and convert it to the tangent space. And how we convert it to some space if we have a transformation matrix? Simply enough, we just multiply the vector with the transformation matrix. And yeah, that's pretty much it. So let me create that. I will create a vector free and call it surface to light, and I do the same calculation as I did in the fragment shader, surface to light. As you can see, I get the light position, I get a vector which pointing to the light position from the current position. Okay, and actually I can copy this as like that. I can copy this right here, but we have to define this uniform variable, the light position, right here as well, because I only defined the light position in the last tutorial in the fragment shader, but I haven't defined in the vertex shader. Okay, and as I said, you can access uniform variable from both the vertex shader and the fragment shader, so there is no problem in here. And now I have a vector which is surface to light, so I only have to do is multiply it by this matrix. So actually we have to create a varying variable which will send back the tangent space coordinate of this surface. So varying, and this is a vector free, and I call tangent surface to light. Okay, the only difference is that this will be in the tangent space, and yeah, that's pretty much it. And I create another one which is tangent surface to view. We have these two vector right here in the fragment shader, because these are the two vectors which are needed for calculate, so surface to light and surface to view. So I have to convert them to tangent space. To convert them to tangent space, basically I just call it vector. So whatever I call it so we can use both the view position and the light position, and we don't get confused about the names. Okay, so the tangent surface to light position, pretty long name, luckily we don't have to write it too much, is equal to the matrix which we have created, the transformation matrix, which convert to the actual tangent space, times this vector which is the normal, which is the surface to light position. So we convert it to a tangent surface of light position. Okay, and let me do the other one. So the vector is equal, again I do the same thing as earlier, normalize minus position, because we again have to use the minus position because the view vector is at 0, 0, the camera is at 0, 0, 0 coordinate. So same thing as in the fragment shader, I use the minus position. Okay, so I have this. So I can calculate the tangent surface to view position, which is again pretty simple. I just multiply the matrix by this vector. Pretty simple, and that's all change actually, I believe, for the vertex shader. So let me go to the fragment shader, and there will be continued. So again, I give it as a varying variable, this tangent position, so I have to copy these, and you know, these will be interpolated across the polygon, and yeah, that's how it's working right here. And now, because we created a variable for basically everything, we could just pretty much make it in free for line. If we don't create a lot of variable for everything, then I can basically just copy this tangent surface to light and place it into here, the surface to light. So I have to renormalize again. The same thing is happening like earlier. So like earlier I showed you, so the normal vector will not be normal length long because of the interpolation. Okay, and the tangent surface to view position, basically I have to just copy this right here, where I use the surface to view. And the last thing we have to do in the fragment shader is actually getting the new normal vector. How we can get the new normal vector? We basically use the same texture access as we did right here, except with the normal texture. So let me create in here texture 2D, and the first parameter is the normal map, and the second is the texture coordinate. We use the same texture coordinate as in case of the normal image, and yeah, that's it. And we have to multiply it by 2. So multiply by 2 and subtract minus 1 from it. So it will be a number between minus 1 and plus 1 every coordinate actually. And I have to cast it to a vector free. I get the x, y, z coordinate from it. We don't care about the alpha component. So I get the x, y, z component from the image, multiply it by 2, subtract minus 1 from it. So it will be a vector which is between minus 1 and plus 1. And that's pretty much the new normal vector, and I'm pretty sure we are finished. I don't know if anything else is needed. So actually, let's try to compile and run this program right now. I'm not sure if we have to compile because most of the modification I did with the shader, but I will try. Okay, and here we go. And as you can see, we already see something, but I'm not sure if it is a wrong or right result. We already have some kind of normal mapping, but actually let me move the light. So I will go to my main file and create a variable. So right here in the top I will create a float L like light position, and I create a boolean as well, so bool b. Okay, and I will show you in a moment what I'm planning to do with these variables. So right here in the display function, if this boolean value is true, then I will increase the light position. So L plus equal, I don't know, 0.1, and if this light position is greater or equal than, for example, 10, then set the b equal to not b. So basically false. And in here in the else I do the same, except I will subtract. So the light will first go to the left, actually the right, and then it will go back to the left if it is less or equal than minus 10. That's basically what it does. So this boolean value will store the current direction of the light, and if the current direction is exceeding some limit, then it will turn back. Okay, and this light position I will just assign it to the x coordinate. So right here in the light pod I will assign the L pod to the x coordinate. Okay, so we have to compile it right now because we modified the program, not the shader. And if I run it, as you can see, it's working, kind of working, but actually it's not working properly. Some reason, I'm pretty sure I have messed up the texture coordinate. So let me go back here and recalculate this texture coordinate. So this is -1 1, which is the left top coordinate, which is actually 1 0. Okay, apparently my texture coordinates were wrong. After a little bit of try and error, I made the right texture coordinate, although I'm not quite sure why these are the good texture coordinates, but these are the ones that work. Anyway, so now if I run the program, as you can see, we have the normal mapping. Quite nice, and it's still just for vertex. That's pretty much it. So I think I will go over the program one last time. So in the main program we don't there is nothing too much going on. Basically I just get the normal map and the image and give it to the program. In the vertex shader we calculate the tangent vector, which I said you might want to give it as an attribute variable from outside. And yes, this one is the calculation, and here I create a matrix from the normal, tangent and bitangent vector, just like I showed you what matrix is needed in order to create a normal map, actually a matrix to transform the vertices to the tangent space. Okay, and right here I just calculate the tangent surface to light and the surface to light vector, as I showed you in here. As you can see, these are the two vectors which are needed to calculate the light. So basically I have to calculate these two vectors in tangent space. We don't care about other things in tangent space because they are not needed in the calculation for the lighting. Right, okay, in the fragment shader I basically get these tangent values, and I use these tangent values to calculate to the surface to light, and the surface to view vector are actually the tangent vectors. Okay, and the new normal vector is actually, we get it from the texture. I have to multiply it by 2 and subtract -1 from it, so it will be a real vector, as I showed you. So it's not 0 to 1 but -1 to 1 vector. And what else? Pretty much that's all I did here. It was a pretty advanced subject, I would say, although we didn't code it that much, but what we have coded is kind of complicated. So you might not understand from this one video, but you may want to read other materials or rewatch the video or something. But this concluded this tutorial. I will cut a scene from a more complicated object right here in a moment. Thank you for watching and have a great day. Okay, here is this brick texture which we have created in game. As you can see, it's not that good, but it's kind of okay because we can make quickly. Alright, let me load what we have created in Blender. There is no normal texture, there is no texture for that, just this normal map. So okay, here is this brick texture. So here it is, what I have created in Blender. There is no other texture for that, just this normal map. So I use this brick texture. And as you can see, it's kind of working. It could be a little bit higher detail model which we have created, but I just want to make it quickly. And it seems that it does actually working. And it really seems like it is some beaver or you see that specular light. Okay, let me load another one. So an example that it work in 3D as well. So I use my OBJ loader to load in a cylinder, as you can see, and I can go anywhere in here, and indeed it's working, as you can see.